In today's lesson, I'm going to talk about the rank of a matrix. Before we can discuss the definition of a rank of a matrix, we have to define some terms. Let us first discuss row and column vectors. Suppose that you have an m by n matrix over here. When we talk about the row vectors of A, those are just the rows of A, and the column vectors of A will just be the columns. The row space of a matrix A is the subspace spanned by the row vectors of A, and the column space of A is a subspace spanned by the column vectors of A. So for example, I have this simple 2 by 2 matrix here. What is the row space? The row space of A is just the span of its row vectors. The span of 1, 3, and 2, 1. Column space of A is just the span of its column vectors. Now here's a theorem that is very useful for us. Two matrices that are row equivalent have the same row space. Why is this true? Recall that row equivalent means that we can get the matrix from the other matrix by performing row operations. However, if we look at our row operations of swapping, multiplying by a constant, and replacing, when we perform these row operations on a matrix, the resulting matrices that we obtain will be a matrix whose rows are just linear combinations of the original rows. We can see that especially for replacing. For example, you have, let's say, R1 plus 2R2. That would be your new R1. So therefore, your new R1 is a linear combination of the old R1 and the old R2. So that is why if two matrices are row equivalent, definitely they will have the same row space. For example, I have this A over here. Its row echelon form would be this one. Thus, according to our theorem, the row space of A, which is equal to the span of 1, 2, and 2, 4, this will just be the same as the span of the rows here of its REF. 1, 2. Well, I can write the 0 row vector here. However, we can drop this, correct? Because if we delete this, the span of 1, 2, 0, 0 is just the same as the span of the row vector 1, 2. Actually, from here also, we can delete this row vector 2, 4 since it is just a linear combination of 1, 2. So in particular, the row space of A is just spanned by one row vector, and that is 1, 2. The theorem that we discussed enables us to find the basis for the row space. How do we get the row space of a matrix? We just get its row echelon form, and the rows containing pivots form a basis for the row space. Why do we get the rows containing the pivots? Because the rows containing pivots will always be linearly independent. And once we have those linearly independent vectors, they will now form a basis for our row space A. Note, however, that not all basis elements that will be obtained using this method will be rows of A. For example, let us look at this A over here and we want to find a basis for the row space. First step, we have to get its REF. You can verify that this matrix is row equivalent to this matrix. What do? We get its pivots, and therefore, the row space of A, I will write it like that, row A, will just be equal to the span of the first row here, 1, 3, 1, 3, 0, 1, 1, 0, and 0, 0, 1. And these three vectors will form a basis for your row space. Note that these two vectors here are actual rows of A. However, the third vector here is not a row of A. So this is what I was saying a while ago, wherein not all the elements will be rows of your original matrix A if we use this method. What we want to do next is to find a basis for the column space of a matrix. It's the most natural thing to do because we just looked for the basis of its row space. Now take note that row operations can change the column space of a matrix. So for example, if we get the column space of a basis for that would be the column vector 1, 2. I will no longer write 2, 4 because 2, 4 is a scalar multiple of 1, 2. So this is the only linearly independent vector. Let's call this B. This is the row echelon form of A. If I get the column space of B, it will be the span of the column vector 1, 0. I no longer wrote 2, 0 because 2, 0 is a scalar multiple of 1, 0. How do the elements of column A look like? The span of 1, 2 would be all scalar multiples of 1, 2. So it is of this form, A to A, where A is any real number, correct? Whereas the span of 1, 0 would be of this form. Let me call it B, 0. These are all scalar multiples of 1, 0. So hence, the column space of A is not the same as the column space of B. Although the column spaces of a matrix and its row equivalent matrix are not the same, what is true, however, is that the dependency of the relationships between the columns do not change if we perform row operations. So for example here in matrix A, the second vector 2, 4 is twice the first vector. This is for A, whereas for B, the second vector 2, 0 is also twice of its first vector 1, 0. So now, if the column space of a matrix and its row echelon form are not the same, how do we get a basis for the column space of a matrix? This is what we use. We use the fact that the row space of A transpose is the same as the column space of A. It makes sense because all we had to do was to transform the columns of A into rows. Transformed its columns into rows. So this column here, when we look at A transpose, it will be C1 transpose, C2 transpose, and C3 transpose. If we get its row echelon form, the rows that we will obtain here will form a basis for the row space of A transpose. How do we go back to A? We just get the transpose of these row vectors. So let me illustrate that here. This is our A, and this is our A transpose. When we get the row echelon form of A transpose, we get this matrix. So therefore, the row space of A transpose will have basis this 3 rows over here. So therefore, the row space of A transpose will just be the span of these 3 row vectors because they are rows. But the row space of A transpose is the column space of A, but then you just turn it into column. So it's going to be the span of, let's turn this to columns. Take note here that the columns that we obtained are not all columns of your original matrix. For the first vector, yes, it is a column of A. However, for the two vectors here, these are not columns of your original matrix A. Here is a summary of what we have obtained. Here are the bases for the row space of A and the column space of A. Again, using our method, not all the basis elements come from your original matrix. Again, from here, the two column vectors here are not columns of your matrix A, and for this one, this third vector here is not a row of your matrix A. What we want to do next is to find basis elements for the column space and row space of A, wherein they are exactly columns and rows of A. In order to do this, we will use the method that we studied in our lesson on dimensions. Recall that in our last video lecture, when we were given a spanning set, we want to turn it into a basis. What we did was that we removed redundant vectors in such a way that when we remove those redundant vectors, you still have the same spanning set, but this time around, the vectors that will result will all be linearly independent. Again, what would be the columns that would be redundant? If a matrix is in row echelon form, the pivot columns of A are going to be linearly independent, and the non-pivot columns are linear combinations of the pivot columns. So for example, I have a matrix A in row echelon form here. The pivot columns would be first, second, and fourth column. This is a non-pivot column. So these three columns here are linearly independent. This non-pivot column 2, 3 is a linear combination of the other three vectors. What would be the coefficients? I will put 2, 3, and 0 here. What about if the matrix is not in row echelon form? This is in row echelon form. It came from this matrix. This time around, my A is no longer the one in REF. However, it is row equivalent to our original matrix. Notice that this vector equation here, what is this vector equation? This is testing for linear independence, correct? Because when we want to get a basis, we want to get the vectors which are linear combinations of the other vectors. And we can get that by forming the equation a1v1, a2v2 plus a(n)(vn), correct? From our previous video lecture. Take note that this will have the same solution as this vector equation. Here, these columns came from this matrix, not in REF, whereas the columns here came from the columns of the matrix in REF. They will have the same solution because they are row equivalent to each other. And therefore, that means that we will preserve the dependence among the columns. So for example, when you solve for the constants there, you will see that a1 is -2, a2 is -3, a3 is 1, and a4 is 0. And those will be the same solutions to these columns here. How do we now use that to find the column space of a matrix? Here is our matrix A, and of course we perform row operations. We get this matrix here. The pivot columns of the row echelon form of A are linearly independent. So where are the pivot columns? Here, here, and here. Those are your leading entries, correct? So you have first, second, and fourth column. They are linearly independent, and we know that these three vectors, the corresponding vectors here, will also be linearly independent because the linear dependence among the columns here will be preserved in your original matrix. Again, take note that this is exactly what we did in our last video lecture, correct? When we were getting a basis for column matrices. So therefore, the column space of A will be spanned by the first, the second, and the fourth column. Let me just summarize what we did there to find the column space. If we have a matrix A, the columns corresponding to the columns of the row echelon form of matrix A form a basis for its column space. So just remember that you do not get the pivot columns of your REF. What you do is you just get an extra step. Get the corresponding columns in your original matrix. Corollary of that is that the dimension of the column space of A is the number of pivot columns in its REF. So here is a summary for getting the basis for your column space. The first method that we discussed was that we transformed A to its transpose, and then we get its row echelon form of B, and the rows of B containing pivots are linearly independent, and then we get the transpose to form a basis. For the second method, in this case, we just use the original matrix A. We transform it to its row echelon form, and we get the pivot columns of B. The corresponding columns of A will form a basis for your column space. So again, this is just a summary. What would be the basis if we just use the row echelon form of A, get the pivot columns, and get its corresponding columns in the original matrix? So it's column 1, column 2, and column 4. This is method 2. And for this one, if we use the transpose of A, we again get the pivots, the leading terms, and therefore what would be your basis here? You will use this rows over here, but you just change it to its columns. So it will be, and this is the basis that you get using method 1. Here is a summary to get two bases for the row space. The first method is using A. We transform A to its row echelon form and get the rows of B containing pivots, and those will form a basis for the row space. The second method is using A transpose as well. We transform A transpose to its row echelon form, get the pivot columns of B, and the corresponding columns of A transpose will form a linearly independent set, and return the columns into rows by getting the transpose. Again, here I have my A. For my first basis here, if I just look at A in its row echelon form, the row space will be spanned by these three vectors. This will be the basis obtained using method 1. And for the second method, we just transform the rows into columns and turn that into its REF. The pivot columns will be here, here, and here. And then get the corresponding columns. And therefore, what would be a basis for this? We now transform this into rows. This is the basis that will be obtained using method 2. Notice that it is very essential that we get the pivots of your matrix. So for example here, in order to get a basis for this row space, we look at the leading terms or the pivots, right? So we have 3 pivots here. So that's why we have 3 elements in your basis for the row space. We also use the pivots in the REF to get a basis for your column space. And therefore, what can we conclude from here? We always use the number of pivots to determine the dimension of the column space and your row space. We can generalize that in the theorem. If A is an m by n matrix, the row space and the column space of A have the same dimension. Since the dimension of the row space and column space of a matrix are the same, we now call it the rank of A, and it's denoted by rank A. So again here, if this is our A, our pivots are here, here, and here. So therefore, the rank of A is equal to 3. This is a useful theorem. The rank of a matrix is given by the number of pivots in its REF. And we have seen this earlier in our example. So therefore, how do we get the rank of a matrix? All we have to do is to transform it to its REF and get the number of pivots. That will give you the rank of A. One more thing before we end with this lesson. What would be another interpretation for the rank of a matrix A? Since the rank of A is the dimension of the row space or column space of A, the dimension of the row space of A, it counts the number of linearly independent rows of A. So hence, the rank of A is the number of linearly independent rows of A. But similarly, since the rank of A is also equal to the dimension of the column space of A, the dimension of the column space of A is the number of linearly independent columns of A. Hence, the rank of a matrix tells us the number of linearly independent rows, and that number of linearly independent rows will always be the same as the number of the linearly independent columns. For example, I have this matrix A. Let us find its rank. We just have to get its row echelon form, and it is given by this matrix. Here are the pivots, our leading entries, and therefore, the rank of A is equal to 3.